MCNP, you have to put it immediately on the root. For Wizard, you can put it wherever you want. And so we will do the exercise tomorrow, both of them. I have two small exercises to propose, but so please install or copy paste the two folder at the right position and be ready for tomorrow to try to do the exercise. So we will pass it. It's the things you have to evaluate, but it's not a problem. We can go through and come back to the exercise on tomorrow morning. Tomorrow afternoon, sorry. So, another possibility to define MCNP geometry is what we call macro bodies. So, macro bodies, in fact, when you look at the different volume you generally used in MCNP, it's always the same. You create box or rectangular parallelepiped. You create sphere or cylinder. These are really I would say the basic pieces to create a MCNP input geometry. So yes, you can have other possibilities. So there is other volume that you can create. But finally, the idea here is to say, okay, finally, what interests me in general is the envelope of a certain volume, well-known volume. And so why not create it immediately, these specific volumes, create the envelope as a specific surface, and say everything which is inside this specific envelope finally is my specific volume, my cell of interest, and everything which is outside, it's or another cells or something that I don't care finally. So this is the idea of the macro bodies. So we will define some envelope which is created taking into account the specific volumes finally we want to use. So these are finally the way to create it. So if you take, for instance, RPP, so it's a regular rectangular parallelepiped. So you have finally 6 surfaces to define, and they are parallel 2 by 2 to a specific axis, or normal 2 by 2 to a specific axis, parallel 2 by 2 to a specific surface. So in that case, for instance, if I define X minimum, Y minimum, and so Y minimum and zeta minimum, I define the corner which is at the down part, the low part of the rectangular parallelepiped. So yes, it's better to draw it, I think. So here. So imagine it's a rectangular parallelepiped. So so means that I have zeta x y. So defining with these 3, I define this point. And with this other, I will define that point. And so finally, knowing that from that point, I have to create a surface which is normal to x, normal to so here, normal to x, normal to so this one down, normal to zeta, and this, so here finally, because I'm from this point, this which is normal to y, and from this point the same, I have no one here in the upper part which is normal to zeta, this which is normal to y, and this which will be normal to x. And so knowing that I need to create this specific volume, and that three different specific surface have to be to pass by to be connected by this specific point, I'm able to reconstruct all my volume. So this is a specific view of the volume. You see that at this moment you don't have to create the different surface. Just using this, so you create only one global surface, which is the envelope of all this volume, and which is defined by these different mnemonic, these different position of x, y, and zeta. And so in that case, even if I didn't have to create a different surface, as you can see, this is a Weisert view. On Weisert, you will see different, different plane. And this, for instance, is the plane 1.5. So 1 because it's related to the macrobodies 1 I created, and 5 because all these planes are receive a number of from 1 to 6. And so it means that even if these planes were not created in a, I will say, normal way, so as I show you to create the plane before, it already exists, and this plane, for instance, goes in, continue, so it's really infinite, and means that if this upper part here, for instance, is the plane 1.5, this plane continue outside the macrobodies, and I can use it, for instance, here, to define, for instance, another cell, or to finish another cells, or to limitate another cells, whatever I want. If I want that another cells is at exactly the same level that the upper part of these macrobodies, I can still use this. It exists outside the macrobodies, even if it's not marked here. And so in that case, to know the number you have to use if you want to use it in another place, you just have to use Weisert in order to visualize the drawing and to visualize what plane. So this plane is, for instance, normal to y, for instance, I don't know, and so you can use it in that situation, in that position. It's that thing that can be taken into account like that. And so you see also that to define the cell 1 using this specific volume, I just have to say that it's inside 1, because in the case of macrobody, we use exactly the same rules than for the sphere. means inside the macro bodies it's minus. I cannot put minus because it's red also, but inside the macro bodies it's minus, and outside the macro bodies is plus. So this is a way to define. It's another way to define a box, for instance. So this exists for other kind of volume. So as it is marked here. So for instance, the right circular cylinder means that the base of the cylinder is a circle, so circular. It's and you have to define in that case the center of the base, so the position of the center of the lower base, the cylinder axis, so here, and the radius, so this dimension. So you see this is one view by Wizard, and this is the view looking at the top of the cylinder, and this is the view looking at a cut along the axis of the cylinder. And so in that case, you have here also, this is the surface. RCC means right circular cylinder. The tree first is, so this tree define the center of the base. This tree define the vector, the axis of the cylinder, and this is the radius of the cylinder. And so this is really easy to do also. The same, the external part of the cylinder still exists here. So you see it's the surface 1.1. So if I want, for instance, to cut something which is just below or in the upper space of the cylinder, I can, for instance, I have here two planes, imagine, and I want to create something which has exactly the same diameter or radius than the cylinder. So I can use this plane also to define a cell, even if this surface which I create regarding that part. But then, yes?
So that's the reason why we are using 1,000 by cells?
Here?
Yes.
In fact, so this value have not to be increased by one in each case. This value, I can put whatever I want. It has just to be increasing, so I cannot put the 20 before the 2, for instance, but I can, whatever. It's not related, it has not to be monotically increased. So by 1, for instance. In general, you see here, for instance, it's 997, 998, 999. Don't care. This is just a number to refer to the surface. It can be whatever I want. So for instance, to use specific range of number to define, for instance, you have a detector. and you have a shielding surrounding all. It means that I have finally three structures here, because my detector will not be just one surface. There is some structure inside my detector. My source can also have some structure inside, and I have my shielding. So, for example, I can say everything which is related to my detector will have a number from 1 to 20. This is the range of my detector. For my source, everything which is between 30 and 50, for instance. And for my shielding, everything which is related to 100 to 120. Even if I don't need 20 surfaces to describe my detector, so I will need, for instance, 3. So I will have 1, 2, 3, even 4. Okay. And after begin my source, it will be 31, 32, 33, something. And after begin my shielding, so it's 100, 101, and so on. It's not a problem. I put it in that way, so it has to be increased in that case. I cannot put 100 before 1, so it's not possible. But there is nothing between 4 and 31. Don't mind, it's not a problem. It's not a number that will serve as a number. It's a number that will serve as a reference. So I don't care. This has no unit. So it's just a reference that I will use to describe or to create my cells here after. And the same for the cells. If I say the cells between 1, I can keep the same ID for the cells that I use for the surface. And normally I will have less cells than surface. So perhaps I will have only 4 cells. In that case, I can have 20 surface, but only 4 cells. So it means that, for sure, in that case, if I keep the same way to indicate it, I will have some, the value will not be continuous, but it's not a problem. Okay?
Thank you.
You're welcome. So here, it's a box. So the difference between RPP and a box is that RPP is always aligned on the axis. So the planes, all the planes are normal to a specific axis, 2 by 2. In the case of the box, no, it can be completely, it can have a tilt, for instance. So it's also a reason why we can use some macro bodies. It's more easy to define them if it's not aligned on one specific axis, for instance. So in that case, we define different values. So for instance, the coordinate of a corner, and this corner is finally the how can I say, the origin, the reference point of my axis. And after, from this element, I will create 3 vectors, each describing one side. And as it is a box, means that these sides are parallel to another. And in that case, for instance, here, if I take something very simple, I have my reference point which is at -1, -1, 1, -1. my first vector is 2, 0, 0, means it's along the x-axis. My second is 0, 2, 0, means that it's aligned on the y-axis. And my third is 0, 0, 2, means it's aligned on the zeta-axis. And so finally, using that way to do it, I create a simple box which is parallel, sides being parallel to the major axis. So yes, it's just to show you, because in that case, using a RPP is more easy and could be more easy to do. But okay. And so in the same, you see that in that case also you just need one surface, which is the global envelope of the box, in order to create the inside volume of the box. So the sphere, so it's quite obvious finally, a sphere, it's already a macro body. So it's a little bit stupid to have it doubled, but okay. MC and P are not always.
Sorry.
So, yes?
Can you please come back on previous
Yes.
slide?
This one?
Yeah. Why we use vectors in the box? Why not planes?
Because here the idea is that this vector is not mandatory a line on the axis. So for instance, imagine that I have also my coordinate like that.
Mm-hmm.
So zeta, y, x, y. And I want to create something like that. So there is a tilt in different, so something like that. Oops.
Mm-hmm.
So I have something which is not aligned to the different axes. Mm-hmm. So in that case here, it's simple because I reproduce a box which is aligned on the different axes. But if I want to have something like that, in that way, I need a vector, and this vector will be the, we will use as coordinate of the vector the projection of the upper corner on the coordinate system. So to define the x position, you will take the value, the length of the side here, multiplied by the cosine of the angle between the vector and the specific axis. So you understand?
So this vector is h of our box,
yes,
or it's just a line that lines in the plane?
The vector is not the age, the height of the cylinder. The vector give, in fact, the coordinate of this last point here. And so this last point here, you can obtain the coordinate multiplying. So for instance here, imagine this is the tilt on the y-axis. So it's the side which is here regarding the y-axis. So this coordinate will be, I will take regarding the zeta-axis is the projection of the position of this point on x, zeta, and y. And so I will have the coordinate of one corner, which will be my reference 1. And from this corner, I will describe 3 vectors. And these 3 vectors will be will give the point, the end of this vector here
Will give us
is the
three
point.
other angles, yes.
And so in that case, I will use the angle, the inclination angle of the specific side regarding x, y, and zeta.
Mm. Mm-hmm.
And this is, so the RPP is used when it's aligned on the axis, and when you want to have this kind of tilt, you need to use this kind of vector. I will show you this with RCC, because in the case of the RCC, you also have the vector which represent the axis, and you will see it just after. I have some figure to show you.
Mm-hmm.
Okay?
Thank you. Uh-huh.
You're welcome. So, as I said, the sphere, it's obvious. Here for the cylinder, means it just, the difference is just that you have not a cylinder, how can I say, a spherical cylinder, but an elliptical cylinder. It's the only difference, but all those things stay the same. You still have, but you need to have the major axis of the ellipse, and the minor axis of the ellipse. But it's more specific, so I will not make a focus on it. Here also the truncated right angle cone. So in that case, you will have two bases, and the cylinder, so not really the cylinder, but the cone between these two bases. And this can be interesting in the case you want to make a link between two pipes. Imagine that you have to describe certain pipes in a factory or in a power plant, for instance, and you have a pipe here with a certain diameter and another pipe here with another diameter, but the normal way, I will say, the mechanical way to connect both will be with that kind of volumes that you can recreate also on MCNP, and there is no easy way to make that kind of things without macro bodies. So this was, I will say, invented to describe some system with pipes, and you need to connect the different pipes. And the same, you have the coordinate of the bottom of the truncated cone. So this part, for instance, you have the axis, description of the axis, and you have the two radius, the small and the larger radius. Finally, it's exactly the same. And so you create also the envelope of the entire system. So the ellipsoid, the same. So I have to say that ellipsoid and elliptical cylinder I never use, and I never see exactly how to use it, but I think that it can be used if you want to describe some human body, for instance. It's more easy perhaps to describe, I don't know, lungs or something like that. But yes, in my case, I never used that kind of volumes. This, for instance, the wedge is very useful. I will just go through some explanation about the wedge. In fact, I don't know if you already have some lectures about medical application. In the case of medical application, in radiotherapy, for instance, there is some devices which is named wedge that you can see here. In fact, it's like something, something you put on a door to keep it open. It's the same, how can I say, the same design. So you have something which is thinner at a certain place and thicker at the opposite part, and it's a volume like that. And the idea is to put it inside the beam in order to modify the shape of the isodose. And so in that case, for instance, you want to have some, you want that your beam, the depth dose given by your beam is higher in that situation, so in that part of the tumor or the body, than in that part. You want to preserve some organ at risk, for instance, that is placed here at this depth, and so you want to give a specific dose to the tumor which is placed here, for instance, and in that case you use these devices, in general in materials which is quite heavy, so will attenuate the beam in a certain, we will have a certain attenuation of the beam. And so in using that kind of things, as you can see, you can modify the shape of the isodose. And so as MCNP is more and more used in the case of modeling medical devices and radiotherapy devices, this wedge was created finally in order to be able to describe as easily as possible this very specific element that is used in medical application. To describe this kind of dose delivery, it's possible using a wedge system. So here I will show you how to describe this element. So if you see, it's in brachytherapy, it's an applicator, gynecological applicator in brachytherapy. So you have the tube here where the source, for instance, iridium 192 can be inserted. And as you see, you have a geometry which is really easy up to this point. Finally, cylinder that keep the tissue at a certain distance of the position of the source in order to preserve some part of the tissue. And you have some applicator, and you see that these applicator have a certain tilt finally regarding the axis, which can be this one. So in fact, in that kind of tube, you put a source which is very small. It's a source of iridium, which can give an extra dose to a specific tumor. And here you have the description of the isodose obtained. So the dot here, the continued line is the value obtained with the real, how can I say, the real devices. It was used. We used the radiochromic films in order to define the dose delivery, so the isodose, and the dots are the calculation by MCNP, so it's a way to compare. And if you want to describe this part of the system, it's difficult using, I will say, a normal cylinder. And it's why, in that case, you see, it's possible to use RCC. And so in this RCC, we have here the position of the reference point in the basis of the cylinder. Here we have the inclination. So this vector, in fact, you have here, it was, yes, it was zeta and y in this value là. So the x-axis is going, it's going out of the screen finally. And so you see that there is no, it's aligned on the x-axis, but there is a tilt regarding the y and zeta axis, and this is finally the length of this cylinder multiplied by the cosine of the tilt angle, and so this gives me the projection of this point on both axes. And this is the signification of the vector. And this is the diameter of the cylinder. The radius of the cylinder. Everything is expressed in centimeter. So I hope that you see better what is the signification of this axis finally. Okay. So, and this is more easy to describe the different the different element if you have this kind of angle finally between your cylinder and your different axes. Okay, so sample 2 it was to change the exercise 1, the definition of the geometry of the exercise 1 by using macro bodies, but as I say, we will do it tomorrow. This is the result. So the last thing I want to see with you today is what we call repeated structure. So I show you the definition of a single pin, so a single fuel element in the water channel. You have an idea of how many of that exist in, I would say, normal power plant, a normal reactor type PWR. No. So what we call a fuel element is a square of 17 per 17, and each of these different water channel are, I will say, occupied more or less by a single fuel rod. So there are a very large number of fuel rods in a reactor. So if I want to define, to model a reactor core finally, you imagine that I have a very, very large number of that kind of rods to define. And you remember some slide ago, I show you the how to define one single fuel element, and it takes quite a lot of different lines to define only one. So, and finally, it's completely stupid to redo the work for one for instance, 1,000 different elements, because all these elements have to be exactly the same. It's the same cladding, it's the same fuel inside, more or less, at least at the beginning of the irradiation, and it's the the same water. So it's, and all these elements have exactly the same dimension. So it's nonsense to do it again. So there is a possibility in MCNP, which is what we call repeated structure. And so the repeated structure means that I will create one element at a certain position, and I will duplicate this element with a certain periodicity. So I have to define the element, my basis finally, and I have to define the periodicity of the reproduction of this element I have created. So means that I will use this lattice card to describe the periodicity finally of the reproduction of my system. My system, it's what I will call universe, and so I will define different universe and fill the universe with specific structure. So there is also two other, how can I say, other command that I can use. It's the like but. So like a certain element but. So means that if everything is exactly the same except a very small part, I can say that everything is equal except one element, and I just give the modification of this specific element. And the TRCL, it means that I can use a transformation. So means that I will translate and or rotate the element. So with that that command, imagine that I have to create a cylinder which is like that, and it's quite complicated because there is a lot of structure inside and I don't know how to do it. But all the structure are aligned, so have the same axis, for instance. So what I can do is to create the system aligned on one axis, so it will be very easy to create. And after, with TRCL, I change the orientation just of the axis to put it like that, and all the structure follow the change of axis. So this is also a very, I will say, smart way to create a structure which is not aligned on an axis. But we can come back to my repeated structure and my universe. So this, I will create, in fact, one universe. Here I say that it's the universe 1. And the universe 1 is finally all the elements of my single fuel rod. So the fuel, the gap, the cladding, the water, all these, as you can see, are created using different planes and cylinder. And so after, I create a cell 5. Cell 5 is finally the cell that contains everything here. And I create in the first time a cell without any materials. As you can see, there is no materials and no density created here. So it's an empty place. And I fill my empty place with my universe 1. So in that case, this is the simple way to do it. I create a cell which is empty, and I fill this empty cell by the universe 1. So just to fill one empty cell by a universe, so it's not needed. I can do it in once. But here, as you can see, it's more complicated. So in that case, my fuel will be in my universe 2. And my universe 1 will be the lattice. So this, imagine the same here, but empty. So just a lattice with all these empty position. And after that, I create this lattice, and I fill my lattice with the universe 2, and in that case, I create the universe 1. So the universe 2 is, with the lattice, is used to create the universe 1. And after that, I have created a place here with an inside and an outside. And the inside will be my the large here, the global thing here. And I fill this bundle with all my universe 1. And so I create all these things here, and I define, so each position will contain exactly the same thing that I create once for all. Here, it's my universe 2, my the package, I will say, fuel, gap, clad, and water. So the same this is very easy, but if you remember what a real reactor is, in fact, in some places here, I don't have fuel rods, but I can have, for instance, control rod, or I will say safety rod. So control rod is to regulate the flux, the neutron flux in the reactor. What we call safety rod is, how can I say, something that it can stop the reactor very quickly if it's needed, because there is some problems in the reactor. There is also some instrumentation. For instance, some, how can I say, some a detector to monitor the flux, or some element to monitor the temperature, or something like that. So there is, in fact, there is some places which are not filled by the control rod. And so this is something that you can see here. So in that case, I don't create control rods or instrumentation, but I just say some of the cells are just with water, and some of the cells are water and cladding and all the things. So I create one universe here, the universe 2, with the fuel, the cladding, and so on. I create a universe 3 with just the water inside, so the cladding and the water, and I put water inside the cladding and outside the cladding, so everything is water except the cladding. And I create my universe 1, it's the lattice, and so in that case, as you can see, I recreate the lattice here. So I don't say that all the lattice is with the same universe, but you see that in some places I put 2, and in some other places I put 3. And if you take a look, everything where 2 is, so when it's filled by 2, it's just the system with the cladding and the fuel. If it's filled by universe 3, it's like here a sort of water just with the cladding. And so you can here, using that kind of structure, you can make 3 or 4 or 5 different, so you can create control rod, you can create a safety rod, you can create an instrument, and you can place it in your reactor, wherever you want, finally, just filling this kind of table. So this is a way to create all the different elements and to use repeated structure. And for sure, it's more easy than imagine if you have to create individually each element like that. You will be crazy after 3 or 4 elements. Okay. So this is the end of the part dedicated to the source, to the geometry definition. So we will end here and continue with MCNP, all the others. So the data block just after so tomorrow in the afternoon, afternoon. Please, so don't forget to install or to copy paste all the elements, so MCNP Envised on your computer, so we can perhaps make the exercise. So you will have to to perform the exercise on your computer. It's important to verify if MCNP can be installed and can run on your computer, and it's also important to make this first small exercise in order to to see if everything is running fine. What I can do for tomorrow is to let you the possibility of presenting and sharing also your screen. So when we will dealing with the exercise, the best is that you can, if you have some problems, you can share your screen with me, and so I can try to help you in order to change and to let all the exercise be done on the computer. Just open the light. Yes, a little bit better. Okay, so you have some question about the things we do today. So no problem. Tomorrow we still have some lectures, and on Friday afternoon, Friday morning, if needed, I can also answer to your question.
Thank you.
It's so have a nice evening, and see you tomorrow.
Thank you. Bye.
Bye.